Alright, today's lesson is about transformers. We'll also be discussing in this lesson electromagnetic induction, alternating current, and Faraday's ring. Alright, let's start by discussing electromagnetic induction, which was discovered by Michael Faraday. His experiment consisted of a bar magnet, and a simple circuit which contained a solenoid or electromagnet and a galvanometer, which is an analog device used to measure the current in a circuit. Faraday tried moving the bar magnet in and out of the solenoid while observing the meter. What he discovered was that when he moved the bar magnet into the solenoid, the meter deflected in one direction, and when he moved the bar magnet back out of the solenoid, the meter deflected in the other direction. However, if there was no motion present, the meter did not deflect. Electromagnetic induction, then, is the generation of current in a circuit using magnets without any physical contact between the magnet and the circuit. Now, another way to achieve this, instead of moving the magnet, is to move the conductor. In this situation, we place the conductor between the north and south poles of a magnet so that it crosses through the magnetic lines of flow in between the magnets. And as we move the conductor up and down, we will notice that again the pointer on the meter deflects in opposite directions. The only way to achieve the deflection of the meter and the creation of current in the circuit is by moving the conductor perpendicularly to the magnetic lines of flow to generate current. If it's moved parallel, it will not generate current. Alternating current is an application of the ideas of electromagnetic induction. We use alternating current to power our homes. Now, alternating current is generated at power plants, for example, a hydroelectric power plant, which uses water to spin turbines. These turbines are then used to rotate a conductor through the magnetic lines of flow between the north and south pole of a magnet. So while the conductor rotates from position 1 to 7, it moves the current in one direction, and as it moves from point 8 to 12, it cuts through in the opposite direction, creating current in, again, the opposite direction. So this is then transferred to a circuit with a load attached to the other end of it through the use of slip rings, which are little pieces of metal which are used to transfer current from a rotating circuit to a stationary circuit. This allows us to use the spinning motion of turbines to power our homes and to power other electrical appliances as well. So now we'll talk about Faraday's ring, which will allow us to practically apply the generation of alternating current. So, Faraday's ring consists of an iron core at the center with a coil of, say, copper wire attached to an alternating current power source. On the other side, there's another coil of copper wire which is attached to a load which needs power. Now, the alternating current travels through the copper wire on the left side, and because it's alternating current, it moves back and forth. And since the iron core is perpendicular to the curled wire, the current alternates directions, cutting through the magnetic lines of force in the iron core, which induces a current into the copper wire on the other side of the iron core, allowing power to reach the load. So if we have lots of power coming from our power supply and we want less power to the load, we are going to have more coils on the left side and less coils on the right side, so that the voltage on the left is higher than the voltage on the right. And this is called a step-down transformer. If we want to have more power or more voltage on one side, on the load side, than we have on the alternating current side, we would have less coils or turns of copper wire on the left and more on the right to increase the voltage on the right. And this is called a step-down or step-up transformer. Alright, let's take a look at some math. So we're going to say that V is voltage, I is current, N is the number of turns in the coil, and P is power. Capital P, that is power. Our subscripts are going to be P and S, little p and S, which P stands for primary and S stands for secondary. And so we're going to go through a couple equations to come up with one equation that will allow us to determine anything that we need to know about transformers. Right, so we take power and break it up into current times voltage of the primary side and the secondary side, and we can represent this so that we have equivalent terms between the two equations, which would be the primary voltage divided by secondary voltage. This allows us to come up with one large equation which combines voltage, current, and the number of turns in a transformer. We can then break this equation up to look at just voltage and current, or just current and number of turns, or just voltage and number of turns, like we would a sine law with a sine law question where we have 3 variables and 1 unknown.